Hi everyone, my name is Ledesma from BSECE 3B, and this is my presentation on ECE 23 Performance Task number 7. So, in this presentation, we will talk about Hamming code. So, here is the short definition of Hamming code. Hamming codes are a family of linear error correcting codes. It can detect 1-bit and 2-bit errors or correct 1-bit errors without detection of incorrect errors. So, Hamming code was invented by Richard W. Hamming codes in 1950 as a way of automatically correcting errors introduced by punch card readers in its time. So, here is the example of Hamming 12-8, which is the 12 stands for bit position and the 8 it stands for encoded bits, which is the bit position is 1, 2, 3, 4, 5, 6, 7, 10, 11 to 12. So the encoded bits is P1, P2, D1, P3, D2, D3, D4, P4, D5, D6, D7, D8. So for example, we must find out if the data word has an error. We must follow its position and its encoded bits position. So for the P1 and P2, P3, P4, P4, which referred as a bit parity coverage, has a value for P1 is equals to 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1. So for P2 has a binary value of 0, 1, 1. So for the section that marked as X is equivalent to 1. And for the section that marked that has an unmarked section, which is this section, has a value of 0. So same for the P3, which is the X has a value of 1 and the unmarked section has a value of 0. Same for P4 or parity 4. So for the example number 1, assume the two essential bit code words are for the calculation for number 1, which is A is code receive 1 equals to 0100 0101 0101, which has an hexagonal value of 455. So its final answer here is its final answer, which is for the code receive number 1 has a D receive equals to 0100 dash 1011 and has a hexagonal value of 4b. So to locate the D receive and P receive, we will just analyze it and compare to the Hamming table and its bit position, which is refer to its assigned bits position, specific bits position. So for the P receive equals to 0, 0, 0, 1 and has a hexagonal value of 1. So for its error, so for the error, we will find out how we calculate the bit error or to find where its bit error position. So here's the answer for the error. Error is in bit number 11. So where is the number 11 bit? So the number 1 here is the number 11 position bit. So for the correct code sent is equals to 0000 dash 0101 dash 0101 and has an hexagonal value of 055. For the descent or dataset equals to 0000 dash 1 rather 011 and has a hexagonal value of 0b. For the parity set is equals to 0001 and has an hexagonal value of 1. So here's the calculation for example number 1. Checking if the data word 01, 000, 10, 10, 101 contains error if it uses Hamming have 8 codes. So here's the given for receive number 1, code receive number 1. So the data word we will just assign to its specific position, which is for the D1 equals to 1, D2 equals to 1, D3 equals to 0, D4 equals to 1, D5 equals to 0, D6 equals to 0, D7 equals to 1, D8 equals to 0. So for the P1 equals to 1, P2 equals to 0, P3 equals to 0, P4 equals to 0. So for the solution, we will just multiply the Hamming matrix to the data given. So to multiply, we must do the specific position given to the Hamming table. So here's the Hamming matrix is multiplied, and here's the value for the given, and here's the solution. So we will just multiply it. So 0 times 0 equals to 0, 1 times 1 equals to 1, 0 times 0 equals to 0, 1 times 0 equals to 0, 0 times 0 equals to 0, 1 times 0 equals to 1, 0 times 0 equals to 0, 1 times 1 equals to 1, 0 times 0 equals to 0, 1 times 1 equals to 1, 0 times 0 equals to 0, 1 times 1 equals to 1. So we will just add, so it is equals to 5. So same process in the solution under, which is the 3, 2, 1, and we will just convert the even value to 0, and for the odd is equals to 1, which is 5 is an odd number, so it has an converted value of 1. So the 3 is an odd, so it is a 1. So number 2 is an even, so it has a converted value of 0, so 0. And the 1 is an odd, so it has equivalent converted value of 1. So the answer is 1101. So this position we will just refer to the Hamming table. So the value of 1101 is located on number 11 position, bit position. So the error is in bit number 11. So 0100 dash 0101 dash 0101 is convert its bit number 11 to correct code sent to 0000 dash 0101 dash 0101. So the number 1 is converted into 0, which is the 0 is the correct. So for example number 2, code received 2 is equals to 0011 dash 0100 dash 1100 with an hexagonal value of 3, 4, and Z. So the final answer is for code number 2 is equals to 0011 dash 1001 with an hexagonal value of 3 and 9 for the D received. For P received is equals to 0100 dash 4 or slash 4 for the hexagonal value of 4. So the error is in bit number 3. So for the code sent is equals to 0011 dash 0100 dash 1000 with an hexagonal value of 3, 4, and 8. For the D sent is equals to 0011 dash 1000 with a hexagonal value of 3 and 8. For the P sent is equals to 0100 and the value of hexagonal value is 4. So we will find out the calculation on the next slide. So checking if the data word 001101001100 contains error if it uses Hamming 12-8 codes. So the data given, so the same process and problem number 1. So here's the solution. The Hamming matrix is multiplied to the given value of variety bit position. So it's multiplied, and here's the calculation, and is equals to 3322, and then converted the answer to even is equals to 0 and add is equals to 1. So 3 is an add, so it is equals to 1. So number 3 also is equals to add, so we convert into 1. So number 2 is an even, so we convert into 0, and number 2 is even also, and it is converted to number 0. So the 1100 parity is located in the number 3 bit position. So the number 3 bit position has an error. So error in bit number 3. So 0011, 0100, and 1100 bit received or data received, code received is been checked, and 0011 dash 0100 dash 1000 is the correct bit, which the one bit error is converted into 0, which is the 0 is the correct bit for bit position number 3. And that's the end of my presentation. Thank you for watching.